For this video, let us present the solution process for a Bernoulli's equation. As mentioned, our Bernoulli equation is in this form: the first order derivative of y with respect to x plus p of x y is equal to your f of x, but it has a certain factor of y to the power of n. The solution here will take a little bit of similarity with linear equation. But first, let's try to come up with a process of converting this into a possible linear equation. So if you have a Bernoulli equation, something like this, your first step is to divide both sides by y to the power of n, regardless of what the value of n is, because n is any real number. Hence, your next step here, it would be this one. As you divide both sides by y to the power 1 to the power of y to the power of n, so you will have here 1 over y to the power of n, or times. Let's just simply multiply instead of divide. Multiply both sides rather. You have here the first order derivative, of y with respect to x. And then you have here plus p of x. And then you have here y over y power of n. You have that, right? Then you will have here f equal to f of x. Okay. The next thing here is, of course, let's express our y in terms of singular exponents. So you will have here y to the power of negative n. You have dy dx plus p of x, and then y to the power of 1 minus n. And you will have here f of x. Okay? The second step of solving this is actually when we let this portion here, because you would like it to become similar to a linear equation, here, y. So we're going to let that as a singular variable z. So that's y to the power of 1 minus, you will have here 1 minus n, right? That would mean this form here, you have p of x and you will have z. You will still have your f of x. But take note, this side has y and d of y. So if you're going to take the derivative of that, you will have your 1 minus n. Okay, take note of that. You will have here y to the power of, let me move this here. This is the process, a little bit complicated. So you have here 1, minus n, y to the power of 1 minus n minus 1, right? When you take the derivative, and you will have your dy. In short, our derivative of z is just equal to 1 minus n y to the power of negative n, okay? And you will have here dy, where this is actually what is this equivalent for, okay? That's the value there. So that means that if you're going to divide both sides, okay, this one here, if we're going to divide both sides with 1 minus n, so we have derivative z 1 minus n, that's actually y to the power of negative n dy, which is again equivalent to this here. In short, you will have here d of z 1 minus n, and you will have your 1 over d of x. In short, your final form now will become d of z over d of x times, you will have here, times, you have your 1 over 1 minus n, plus, you have p of x, and you have here your z is equal to f of x. Now, to make this linear, we don't want this here, because the form of the linear must actually be this form, equal to f of x without any other exponent of y, or for y there, in this case z. So you'll be multiplying the third step here, okay, multiply 1 minus n on both sides. So you will have the final form d of z, d of x, plus 1 minus n p of x z. Take note that n is any number, so this would be constant. Okay, you have here is equal to 1 minus n f of x. Again, n is any number, so that would be constant. This is now in a form of a linear equation, but instead of y, you will be getting z. So from this point onwards, you're going to use the process for linear equation, where we need to use the integrating factor, but this will be our entire p of x, right? Whatever that value is, and this will be your entire f of x, depending on what would be our n, because it also be our coefficients will be affected regardless of what that n is. Imagine if it's just equal to 2 or equal to 5 or negative 10. So your p of x and f of x has different coefficients. So still get to use the integrating factor, and then you will going to use the solution for this. By the way, z, not y anymore. You will have the integrating factor of x, f of x, dx. So once you will solve here your z, something equivalent here, this time you would return now to this value, because what you're solving is not z, you're solving is actually for y. So once you will get the value of z, return to this equivalence so that your y will be reintroduced here, and together with the exponents and notations and coefficients, you will also be revising your result here. We will have examples on solving Bernoulli's equation using this process, but what my point here is that from a Bernoulli equation, transform it into an equivalent linear equation so that you can duplicate the process of linear equation, but then in your equation with respect to z, but then again you will be returning to y, because z is not in the given but it is y, just represented by this z. Again, please stay tuned for some examples for this. Thank you very much for watching.